Hello friend, we will start the fourth topic from theoretical chemistry, semester 4, geology development. The name of the topic is kinetic and thermodynamic control of reaction. In this topic, we will discuss the 5 reactions. The very first with nitration and sulfonation of naphthalene. After that, heating, then Friedel-Crafts, then ionization, and last one is the reaction. Today we will start with nitration and sulfonation of naphthalene. After that, heating, and lastly Friedel-Crafts. Then you can see on the screen the naphthalene. Naphthalene is a fused ring. The two base rings are fused with each other to produce naphthalene. Naphthalene is an 8-member ring containing molecular formula C10H8. This is hydrocarbon. This is hydrocarbon with its resonance structure. If you can see here, the bond length of carbon-carbon at naphthalene molecule, you can see here you can see here 1.42 angstrom unit. 1.42 angstrom unit. This is 1.36 angstrom unit and this is 1.40 angstrom unit, and the fuse system is 1.39 angstrom unit. If we compare with these, carbon-carbon in ethene is 1.54 angstrom. Carbon-carbon in ethylene is given by 1.34 angstrom, and carbon-carbon in benzene is same in 1.40 angstrom. But because of the resonance structure, this bond length will be changed as per the this. Then you can see the first example of nitration of naphthalene. Then this is your naphthalene. The requirement of nitration, the reagent is nitrating mixture. That is nitric acid plus sulfuric acid. Then two types of product will form. That is alpha nitronaphthalene, we call as 1-nitronaphthalene, and beta nitronaphthalene, also called as 2-nitronaphthalene. Then assume that the nitration at position 1, then you can see the various resonance structure. You can see the various resonance structure. Then it can produce 7 total resonance structure. Between these 7 total resonance structure, 4 of the structure preserve the aromaticity of the one of the ring. इथे जर तुम्ही बघितला तर जर आपण अल्फा पोझिशन जर कन्सिडर केलं नायट्रेशन झाली तर इथे आपल्याला 7 रेझोनन्स स्ट्रक्चर पॉसिबल झाले आणि या 7 पैकी 4 जे रेझोनन्स स्ट्रक्चर आहेत त्यामध्ये 2 पैकी एकाची अरोमॅटिसिटी प्रिझर्व केलेली आहे. अरोमॅटिसिटी म्हणजे तुम्हाला आता माहिती आहे तर ती प्रिझर्व केलेली आहे. आपण बघूया पहिलं एक्झाम्पल कन्सिडर करूया. Consider Korea this structure. अल्फा पोझिशनला नायट्रेशन झालेलं आहे त्यामुळे सेकंड नंबरच्या पोझिशनला कार्बन काय करेल तो काय करेल स्टॅबिलाइज. त्यामुळे पॉझिटिव्ह चार्ज मला इथे मिळेल. हा पॉझिटिव्ह मिळाला चार्ज की हा इथं बॅलन्स करेल तर मला पॉझिटिव्ह चार्ज इथं मिळेल पुढच्या स्ट्रक्चरमध्ये आहे ते. त्याच्यानंतर सिमिलरली दिस त्याच्यानंतर परत बॅलन्स केला तर आपल्याला इथं मिळेल. त्याच्यानंतर परत हा आतमध्ये गेला मायग्रेट करून तर आपल्याला इथे मिळेल आणि अशा प्रकारे मला एकूण 7 स्ट्रक्चर मिळाले. Between these 7 structure, here first, then second, then third, and this is fourth. These 4 structures, if you can see carefully, a dark benzene is shown, means the aromaticity is preserved. After, you can see the next one. Yes, nitration at beta position. Then what happened? We got 6 resonance canonical structure. Between these 6, only 2 canonical structure who shows or who preserve the aromaticity. Who preserve the aromaticity. 2 of these, 1 and 6, we can see carefully in this ring, the aromaticity is maintained. So that attack at C1 position is favored because it forms more stable intermediate. The major product is 1 nitronaphthalene and the minor product is 2 nitronaphthalene as per the theory. Again, we can find out the sulfonation of naphthalene. Sulfonation of naphthalene. In this case also, if we can maintain some temperature condition as low, then we got alpha naphthalene sulfonic acid. And if we can increase some temperature or double the temperature as we use at the lowest temperature, then we got the beta derivatives of naphthalene, or we observe sulfonation of naphthalene at beta position. If we look at the intermediate leading to isomers, we can draw the same structure, and again at our alpha position, the 4 compound, 4 canonical structure preserve the aromaticity as compared with the beta isomer. Here, the naphthalene. The naphthalene, one isomer produced with lower energy will produce the lowest energy, so that the compound formed at 1 naphthalene, 1 sulfonic acid results from the kinetic product, kinetic controlled product. And as at the higher temperature, some energy is consumed by naphthalene, then the 2 isomer will form. Naphthalene to sulfonic acid will form. In the next slide, we will see the alpha position sulfonic acid at alpha position or 1 naphthalene sulfonic acid is product form is less stable because sulfonic acid is a very bulky group, and at 8 number proton and sulfonic acid will repel to each other, Hence, the product form of 1 naphthalene sulfonic acid is less stable. When consuming some enough energy or consuming some higher energy, then the conversion of less stable product to more stable product formation takes place. Because the more stable product is 2 naphthalene sulfonic acid, the position of sulfonic acid at beta to naphthalene produces less repulsion with 1 positions hydrogen and 3 positions hydrogen. Hence, the product form 2 is more stable. The product form first, that is less stable, 1 naphthalene sulfonic acid, produces fastly, but the nature of product is very unstable because of the repulsion between adjacent proton, and it rearrange or after consuming some more energy, it will rearrange or to produce most stable compound, that is 2-naphthalene sulfonic acid. If you compare the energy profile diagram of this sulfonation of naphthalene, here the black is for beta and red is for alpha. If you compare the energy profile diagram, then the graph shown by red is at lowest energy level and fastly formed. But the energy level of the reactant, this is the energy level of reactant and the energy of product is very difference is very small. The difference is very small. Hence, the less stable product will again form the reactant and acquire some higher energy level that is shown by black. It will produce the most stable derivatives, that is the beta isomer, and the beta isomer is most stable produced at 160 degrees Celsius. This is the in general sulfonation of naphthalene. At lowest temperature, alpha product will form. At higher temperature, beta product will form. This is the nitrating and sulfonation of naphthalene. After that, we will start the Wittig reaction. Also, Wittig reaction shows thermodynamic and kinetic control reaction. Then, before start the Wittig reaction, what is meant by Wittig reaction? There is some difference between Wittig rearrangement and Wittig reaction. Wittig rearrangement is the conversion of ether to alcohol, and here the Wittig reaction is the Ylide is used, the conversion of carbonyl group into the alkene. This is the Wittig reaction in presence of ylide, that is phosphorus ylide. The Wittig reaction I will discuss here. The Wittig reaction is also called as Wittig olefination reaction. In Wittig reaction, the conversion of aldehyde or ketone in alkene in presence of triphenyl phosphonium ylide. It is also called as Wittig reaction. This is the triphenyl phosphonium ylide, that is Wittig reaction. It will convert the carbonyl group into the ketonic group. The carbonyl group is converted into the alkene. Then the reaction. Here also I will repeat the reaction. The carbonyl group, that is ketone, is used, and here triphenyl phosphine ylide is used. Then it produces alkene with loss of triphenyl phosphine. The mechanism. Here the phosphorus and carbon bond we call as ylide. The charge separation is the carbon having higher electronegativity, and it will attack to the carbonyl group. It will attack to the carbonyl carbon because the carbonyl carbon is highly electron deficient. We produce oxophosphatane derivative, and this oxophosphatane derivative rearrange to produce alkene with the loss of triphenyl phosphine, trialkyl phosphine. The negative charge species firstly attack the electron deficient carbon, then after that O- will produce. This O- again reacts with phosphorus because of the phosphorus is an electron deficient to form oxophosphatane complex. This oxophosphatane complex will rearrange to produce the alkene. Early mechanism or some book published the intermediate butane will form. After some slide skipping, we will start the next part, the rate determining scale. The rate determining scale. If you can see here, the following are the two examples. One of the example is aldehyde and second one example is the carbonyl. The aldehyde and carbonyl group produces alkene, that is E-alkene. But if you compare the proportion of the product, then aldehyde produces 80%, and ketone produces less yield. If you can see the explanation, then at the rate determining step, the initial addition of carbonyl group, to form oxophosphatate, More electrophilic carbon react more readily. The more electrophilic carbon compound reacts more readily. In this example, carboethoxymethylene triphenylphosphorine fairly reacts with aldehyde, but can do poor in reaction with less reactive carbon of ketone, because it is found that resonance stabilized aldehyde gives predominantly the E alkene. If we can compare the aldehyde having stabilized aldehyde, that is resonance stabilized aldehyde, produces E isomer. You can know EZ nomenclature. EZ nomenclature. The resonance stabilized aldehyde produces E alkene. If we can compare, this is your resonance stabilized aldehyde and this is your aldehyde. Then this aldehyde and this group produces a carbon-carbon double bond, as here shown by greener line. Again, if you can see here, this is your resonance stabilized aldehyde, and here is your aldehyde. Then this negative charge species will attack this carbon group to produce this group, that is E selective, shown by greener. This is again your triphenyl phosphine stabilized aldehyde, produces reacts with benzaldehyde, produces again E alkene. Then question arises, why E stereoselective produces with stabilized aldehyde? Then you can see here an unstabilized aldehyde. If we can use an unstabilized, the stereochemistry of alkene product is determined. The stereochemistry of intermediate oxophosphate produced in the stabilized aldehyde must be anti. इथं जर तुम्ही कंपेअर केला की स्टॅबिलाइज इलाइड आणि तुमचा कार्बोनिल ग्रुप, हे दोघांचे ऍडिशन होताना ते दोघांचे ऍडिशन कसे होतात, अँटी पोझिशनला जातात. कधी तर जेव्हा इंटरमिडिएट ऑक्सोफॉस्फेट फॉर्म होतो तेव्हा. त्यामुळे ऑक्सोफॉस्फेट इंटरमिडिएट फॉर्म होतो तेव्हा ते अँटी पोझिशनला गेल्यामुळे ते काय जेव्हा अल्किन फॉर्म करतील तेव्हा त्याची डिरेक्शन कशी असणार आहे, की आयसोमर असणार. आणि जेव्हा तुमचा अनस्टॅबिलाइज इलाइड घेताय तेव्हा ऍडिशन होत असताना इलाइडची आणि कार्बन ग्रुपची किंवा सिंग ऍडिशन होती, त्यामुळे आपल्याला झेड आयसोमर ऑब्झर्व होतो. तर तुम्ही इथं एक्झाम्पल बघितला तर हा स्टॅबिलाइज इलाइड, हा निगेटिव्ह चार्ज, हा पॉझिटिव्ह चार्ज. हा पॉझिटिव्ह चार्ज तुमच्या कार्बन ग्रुपवरती अटॅक होत असताना आपल्याला हा तुमचा R1C++O आणि हा CH2 हा पोझिशन आणि हा तुमचा उरलेला R2 हे दोन्ही अँटी पोझिशन. आणि जेव्हा हे डिकंपोज होईल किंवा हे जेव्हा रिअरेंज होतील तेव्हा काय होतील, हे दोन्ही ग्रुप एकमेकांच्या अपोजिट साईडला, एकमेकांच्या अपोजिट साईडला जातील. याचा अर्थ काय होईल, ही आयसोमर फॉर्म. आणि जेव्हा आपण स्टॅबिलाइज आणि अनस्टॅबिलाइज इलाइड घेतो, स्टॅबिलाइज इलाइड घेताना आपल्याला काय मिळतो, आयसोमर ई आयसोमर, आणि अनस्टॅबिलाइज घेतो तेव्हा आपल्याला मिळतो झेड आयसोमर. आता इथं परत तुम्हाला एक दाखवलेला आहे, हा जो तुमचा स्टॅबिलाइज इलाइड आहे तर त्याच्यापासून मिळणारा जो काही प्रोडक्ट असतो तो मोस्ट स्टेबल प्रोडक्ट म्हणतो, दॅट इज थर्मोडायनामिक कंट्रोल. बिकॉज अँटी ऑक्सोफॉस्फेट जो फॉर्म होतो त्याची स्टॅबिलिटी अक्वायर करायची असेल तर 4 मेंबर रिंग आहे, त्यात फॉस्फरस आणि ऑक्सिजन आहे. हे हायली स्ट्रेन कंपाऊंड, हे हायली स्ट्रेन कंपाऊंड त्याची स्टॅबिलिटी अक्वायर करायची असेल तर दोन बल्की ग्रुप जर एक पोझिशनला असतील तर त्याच्यामध्ये स्टेरिक रिपल्शन होणार, त्यामुळे स्टॅबिलिटी डिस्टर्ब, ते फॉर्म होणार नाही. त्यामुळे जर ते अँटी पोझिशनला गेले तर ते इझिली फॉर्म होईल. इट इज if you can see the anti-oxophosphatin, then but it now seems like that form stereoselective under kinetic control. The difference from the alkyl substituted unstabilized alide lies to repulsion experience between polarized carbon between aldehyde and electronegative stabilized group, that is ester. If you can see here the mechanism, this is your elide. When phosphorus and carbon shows double bond, sometimes phosphorus and carbon shows single bond. With the charge, phosphorus becomes positive and carbon becomes negative. Then this bond, P3P and your oxygen, this negative charge attack to this carbonyl group. Then what happened? Partially bond formation takes place, and this oxygen and this carbonyl oxygen, these two oxygen are electronegative species. The electronegative species. When these are in different direction, then electronegative groups are repelled to each other. Okay, then E3P and pH, the greener part, also the large substances are keeping the away. Hence, the oxyphosphate becomes antiplanar stereochemistry, antiplanar structure. Hence, the stabilized lead, if you can use, then this type of derivative we can also. Sometimes if you are unstabilized lead, you can use the stereochemistry of formation of syn oxyphosphate with unstabilized lead. These two groups are, because here there is no oxygen atom, that is electronegative atom, then it cannot repel with this pure aldehydic oxygen group. Hence, these two groups becomes in the same direction, that is same direction, so that after rearrange the produce alkene having the same alkene. Again, why the syn oxyphosphate favor with unstabilized lead? Yes, why the oxyphosphate favors unstabilized lead? Again, if you can compare the addition of lead with carbonyl and using perpendicular approach, then the large substituents are kept away from each other. Large substituent means R group and phenyl group are in opposite direction, as well as carbonyl, phosphine and phosphorus are in opposite direction. Here only one oxygen atom is there, hence no carbonyl group, that is stabilizing agent. Hence, the two groups produces syn direction in the oxophosphate. Hence, we can form the product as the same isomer. This is unstabilized phosphorus halide reacts with this aldehyde, produces ZR. Then the next one reaction is Friedel-Crafts reaction. You can study Friedel-Crafts reaction at semester first, MSc part first. In Friedel-Crafts reaction, the Friedel-Crafts reaction we can produce the substitution reaction of aromatic compound. The substitution reaction of aromatic compound. In this reaction, the aromatic compound reacts with alkyl halide in presence of Lewis acid, produces substituted aromatic compound. The Friedel-Crafts reaction having two types, that is Friedel-Crafts alkylation and Friedel-Crafts acylation. Also, this is the mechanism of Friedel-Crafts reaction. The very first is the your alkyl halide. Alkyl halide come in contact with Lewis acid, produces alkyl halide Lewis acid complex, and these are equilibrium with its ion pair. The aromatic compound reacts with ion pair to produce sigma complex, and this sigma complex can stabilize by resonance structure. And after that, the positive charge is stabilized by abstracting a proton by the Lewis base, and we can form the Lewis acid will regenerate at the end of the reaction with substituted aromatic compound as our goal. Again, if alkyl halide is tertiary, then reaction starts with the formation of carbocation, and this carbocation acts as electrophile. With primary alkyl halide, the electrophile is an alkyl halide Lewis acid complex, with positive polarized charge. The last slide, you can see the mechanism. In this case, the electrophile is alkyl halide and Lewis acid. But in this example, the carbocation form and carbocation is acts as electrophile. In this again, we can use alkyl halide is tertiary because tertiary carbocation is more stable. In the step first, this is tertiary alkyl halide reacts with Lewis acid produces tertiary carbocation, and this tertiary carbocation attacked by benzene and produces carbocation in the benzene, and this can be stabilized by its resonance structure. And at step 3, one of the proton is captured by Lewis acid produces with substituted benzene. Then Friedel-Crafts dealkylation. Alkylation is the reversible so that the reaction is thermodynamically controlled. When we react benzene with alkyl halide, the reaction is thermodynamically controlled. But monosubstituted benzene usually gives meta-alkyl derivatives since this is thermodynamically more stable. The principle may be usefully applied. For example, benzene reacts with ethyl bromide. It will produce 135 triethyl benzene is the product. Because of the steric hindrance, it will be rearranged to meta position. Generally, alkyl substituents are electron donating. It will produce orthopara positions compound, but because of the rearrange or acquires some more stable compound to produce meta substituted. And this is thermodynamically controlled. But tertiary alkyl group during alkylation, when heated with your lastly step form HCl AlCl3, it will dealkylate the substitute. If we can produce the aromatic Friedel-Crafts alkylating reaction when at the last step produces HCl AlCl3 complex, this will be dealkylate the aromatic compound and produces the previously your benzene. Okay, lastly, we can study the application of this particular case. Suppose we want to convert benzene into orthomethyl acetyl. This conversion can be carried out as follows. First, we can take as benzene, and benzene reacts with alkyl halide, that is methyl chloride, in presence of Lewis acid, that is anhydrous AlCl3. Then we got toluene. This toluene will react with tertiary butyl chloride in presence of AlCl3. Then methyl propionate orthopara derivative. It will migrate tertiary carbocation to the para position. That is, reaction takes place only at para position because of the steric hindrance, not at ortho position. After that, Friedel-Crafts acylation reaction is there. That is acyl chloride and Lewis acid, that is AlCl3. Then the acyl derivative will join at position 2 of the methyl group because the ortho position of methyl group is less steric hindrance as compared with tertiary butyl compound at para position. And when you can use HCl plus AlCl3, then dealkylation reaction takes place and it dealkylates the tertiary butyl group and to produce the orthosubstituted product as the main product. This is the application of Friedel-Crafts reaction. Okay, thank you. In this part, we have completed the three reactions. Tomorrow we will be discussing the annualization reaction, and the disorder reaction. If any doubts or any problems, then send me the message. I will solve your all type of doubts. Okay, thank you.